Good day. My name is Julio Sebastián de la Trinidad Rendón, and I'm going to present Hybrid ADRC-CBF controller for chaotic system synchronization. This is the outline of the presentation. We have the introduction, challenge, ADRC-CBF, hybrid architecture, and our experimental results to end with our conclusions and future work. What is the problem that we are attempting to solve? Controlling chaotic systems. We are attempting to synchronize two integral cubic controller oscillators in a master-slave configuration. The master evolves freely and the slave must track the master under significant disturbances and uncertainty. Why does this matter? Because these kind of systems can be used to secure communications as an encryption preventive. We could need coupled oscillator and maybe even as a benchmark difficulty due to the ICC sensitivity due to the cubic nonlinearity. What is our proposed solution? We propose a hybrid controller which combines the three elements ADRC, which is active disturbance rejection control, which estimates and cancels a lumped total disturbance online. Also, we could use CBF, which are control barrier functions, which enforce state and effort constraints by construction. Finally, we would solve CBF via quadratic programming, which computes the closest safe control to the nominal ADRC command. What are our ICC system dynamics? The dynamics are given by the equations on screen, where we have the cubic nonlinearity that induces chaotic behavior. On the right, we have the chaotic attractor in a 3D plot. We have three major challenges. We have unknown nonlinear dynamics given by the chaotic term, which cause with a small mismatch a large tracking error. We also inject external disturbances, which are Gaussian noise, step disturbances, and sinusoidals. We have for safety requirements that E1 must be smaller or equal to 0.01, E2 must be smaller or equal to 0.1, and U must be smaller or equal to 100. And the question is why traditional controllers fail. We tested several of them. For example, the PD controller, it does not have disturbance rejection. It does track, but it has many constraint violations given by the later CBF. We attempted feedback linearization, which requires accurate models but may be brittle under mismatch or noise. Pure ADRC has a strong tracking but does not have explicit constraint enforcement, and pure CBF is constraint focused but does not have any disturbance estimation, which causes degraded tracking. Thus, a hybrid design is required to combine robustness and constraint enforcement. Then, what is the core idea? Rather than relying on precise modeling, ADRC lumps unknown dynamics and disturbances into a single total disturbance, which is sigma of t, given by the equation on screen, where sigma aggregates nonlinear mismatch, linear coupling, and external disturbances. Our approach is to estimate sigma online and cancel it in the control input. Our extended state observer is a third order observer which estimates position error, velocity error, and total disturbance, given the dynamics of the observer in screen, with bandwidth parameterized gains, which are pulse at minus omega O, which is equal to 50 radians per second. We have our ADRC control law, which uses sigma hat, which is the nominal ADRC command, and cancels the estimated disturbance and applies PD terms given by the equation with U nominal. PD gains are given by Kp equals 25, Kd equals 10, and omega c, which is 5 radians per second. We have that the disturbance cancellation approximately yields a double integrator error channel given by the equation in screen. We also have a safety problem. The ADRC minimizes tracking error but may violate constraints which are state bounds and actuation limits. That is why we are including control barrier functions, which are a function h of x greater or equal to 0, which defines a safe set. Safety is enforced via the equation given in the screen, which provides forward invariance. which means that starting safe implies remaining safe. We have two barriers in our hybrid system. We have the position barrier, which is the tracking bound, which is a relative degree 2 and uses a high order CBF, given the auxiliary function on screen. We have also an energy and velocity barrier, which is our effort proxy, given by the equation in the screen, which is of relative degree 1, which directly constrains control. We have also the hybrid QP formulation. We require computing the control U closest to U nominal while enforcing the following constraints given by the equation, which are subject to actuator limits, hard limits of minus 100 and 100, position HO-CBF, and our energy CBF. We also have a term for slack non-negativity. We manage this as feasibility via soft constraints, which are the slack. These quantify constraint relaxation when the QP would be otherwise infeasible due to saturation, for example, of the actuators. As a practical effect, large penalties keep approximated to zero whenever possible. When constraints conflict with actuator limits, the solver returns to the least violating admissible action. The outcome we have is graceful degradation instead of infeasibility. Our complete control flow starts with our extended state observer, which estimates the disturbance of the system. It gives it to the ADRC, which outputs a U-nominal control command, which is passed to the CBF QP safety filter, which solves towards a safe command towards the plant. We evaluated several configurations, for example, ADRC plus a position barrier, which enforces the position to limit E1. ADRC with an energy barrier, which enforces H energy to limit E2 towards the system, which is the control aggressiveness. We finally tested ADRC plus dual barriers, which is a hybrid approach combining the previous two. We enforce both constraints simultaneously, which is the tracking bound and the effort proxy. Our results are given by a simulation horizon of 50 seconds with the previously mentioned disturbance and our tracking bound, which is Emax equals to 0.01, and our actuator, which requires a U of less or equal to 100, and we tested the control speedy ADRC, ADRC-CBF for position, ADRC-CBF for energy, and the ADRC-CBF approach, of which the hybrid dual barrier yields the fewest and least severe violations, as given in the table. The key findings: we have dual barrier hybrid that improves constraint adherence. We have 29% fewer violations versus the pure ADRC approach. We have approximately 30% lower violation severity and approximately 30% faster recovery time. The position-only CBF is the most conservative during transients. It does have more violations than other ADRC-based variants, which indicates transient overshoot and aggressive corrective action under disturbance. We have also slack activations, which indicate occasional constraint conflict. We have that the hybrid approach uses a slack when saturation and safety constraints complete. It also maintains feasibility and reduces failure cases. What we have achieved with this, we have constructed a hybrid ADRC-CBF synchronization network, which provides active disturbance rejection with the ADRC, and the CBF QP enforces constraints with minimal deviation from nominal control. We also have constraint-aware performance under disturbance, which reduces constraint violations and recovery time relative to ADRC-only baselines in the tested scenarios. We also have an implementation-ready structure, which means we have real-time QP filtering on top of a tunable observer-based nominal controller. Our future work would be a multi-agent synchronization, which are networks of oscillators with distributed or compositional safety constraints. We also want to test with other chaotic systems such as Lorentz-Rossler-Chen and hyperchaotic variants. We want to also construct adaptive tuning, which is online selection of omega O and omega C, and barrier parameters based on operating conditions. Finally, richer constraints such as time-varying bounds and state-dependent varied design. I want to acknowledge the support by Cecity Scholarship and thank you so much for your attention.